In this lesson, we're going to explore eliminations, focusing on the E1 and E2 mechanisms. Elimination is one of the 6 fundamental organic reactions. In an elimination, a molecule is expelled from another molecule to form a new pi bond. Most eliminations are beta eliminations, which involve the removal of a leaving group and an adjacent beta hydrogen. So here I have an abstract example. On the right carbon, we have a leaving group represented by X, and on the adjacent or beta carbon, a hydrogen atom, and because it's on a beta carbon, it's referred to as a beta hydrogen. When treated with a base, the leaving group and the beta hydrogen are removed, expelling a molecule of HX and forming a new pi bond. Below is a more concrete example, reacting bromoethane with hydroxide. You can see that HBr is removed and forms ethene. The hydroxide base has accepted the beta hydrogen to form water, and the leaving group has been expelled as bromide. Elimination reactions are reversible, and the reverse of an elimination is actually an addition reaction. Eliminations are often difficult to achieve because of the formation of a pi bond. The equilibrium can be pushed forward by the expulsion of a good leaving group or by the use of a strong base. In general, equilibrium will favor the formation of the weaker, more stable base. In the first example, we can see that hydroxide is the base and chloride is the leaving group, and since chloride is more stable than hydroxide, the elimination is favored and equilibrium lies to the right. In the second example, we can see that chloride would be acting as the base and hydroxide as the leaving group. And since hydroxide is less stable than chloride, the elimination fails and equilibrium lies to the left. There are actually several mechanisms by which elimination can occur. We're going to restrict our discussions to just 2. First is the E2 mechanism, which stands for bimolecular elimination. Just as we saw for the SN2 nucleophilic substitution, bimolecular indicates that there are 2 molecules involved in the rate-limiting step. The E2 mechanism is a concerted one-step mechanism. In this case, we see hydroxide acting as the base. The hydroxide removes the beta hydrogen, pushing the CH bonding electrons towards the neighboring carbon, forming the pi bond and expelling the leaving group. An important aspect of the E2 mechanism is that it requires a paraplanar relationship between the beta hydrogen and the leaving group. In this context, paraplanar simply means that the 2 groups need to be in the same plane. Because of free rotation, there are actually 2 conformations in which the leaving group and the beta hydrogen can be in the same plane. The anti-paraplanar conformation places the leaving group and the hydrogen anti to one another, pointing in opposite directions. The syn-paraplanar conformation places the leaving group and the beta hydrogen syn to one another, pointing in the same direction. It turns out that reaction of the anti-paraplanar conformation is considerably faster than the syn-paraplanar conformation. In the syn conformation, expulsion of the leaving group is impeded by the base, which needs to approach the reactant from the same side. The syn-paraplanar conformation is also an eclipsed conformation, making it considerably less stable than the anti-paraplanar conformation. That means that at equilibrium, there will be considerably more anti-paraplanar conformation than syn-paraplanar, and the higher concentration leads to a faster reaction starting from the anti-paraplanar conformation. This phenomenon leads to an interesting consequence with respect to the stereochemistry of the products. In this example, you can see that there is only one beta hydrogen adjacent to the leaving group, and that means there is only one conformation that will place the hydrogen and the bromine into an anti-paraplanar arrangement. When the reactant has only one beta hydrogen, the stereoisomer formed from that anti-paraplanar conformation is the favored product stereoisomer. In this example, you can see that reaction of the anti-paraplanar conformation led to a less stable Z-alkene as the major product. When the reactant has only one beta hydrogen, the only way to determine the stereochemistry of the product is to draw the reactant with the leaving group and the beta hydrogen placed anti-paraplanar and observe where the substituents are in space relative to one another. In this case, we can see in the reactant that the 2 ethyl groups are pointing in the same direction, and that means that in the product, they're going to be pointing in the same direction as well, in this case leading to a Z isomer. Determining the major stereoisomer formed in an E2 reaction when the reactant has 2 beta hydrogens is simultaneously simpler and more complex. The complexity arises because there are now 2 beta hydrogens, each of which can be placed anti-paraplanar to the leaving group. So in this example, I have a tertiary alkyl halide undergoing an E2 elimination. It's important to recognize that the 2 drawings on the left are the exact same molecule. The drawings represent two different conformations of that molecule. In the top conformation, the green hydrogen is placed anti-paraplanar to the bromine leaving group. Because the two ethyl groups in this conformation are pointing in the same direction, they'll end up in the same direction in the product, giving rise to a Z isomer. When the red hydrogen is placed anti-paraplanar to the leaving group via free rotation, the two ethyl groups are now pointing in opposite directions, and that means they'll retain that spatial arrangement in the final product, giving rise to an E isomer. Because the lower conformation places those two large ethyl groups far away from each other, it's going to have less steric strain and be more stable than the top conformation. Because it's more stable, there will be more of this conformation at equilibrium, and that higher concentration will lead to a faster reaction. So while the explanation is complex, the outcome is actually quite simple. When E2 occurs on a reactant that has two beta hydrogens, the more stable alkene stereoisomer will be the major isomer formed. The second mechanism of elimination we're going to look at is the E1 mechanism, which stands for unimolecular elimination. Again, just as we saw with the SN1 nucleophilic substitution, unimolecular indicates that there is only one molecular species involved in the rate-limiting step of the reaction. If we look at the mechanism, we can see that it occurs in two steps. In the first step, the leaving group leaves to form a carbocation, and that means that the first step in the E1 mechanism is exactly the same as the first step in the SN1 mechanism. Once the leaving group leaves, a base removes the beta hydrogen from the carbocation to form the pi bond. The stereoselectivity of the E1 mechanism is actually quite straightforward. After expulsion of the leaving group, removal of the beta hydrogen can only proceed when the CH sigma bond is aligned in the same plane as the empty p orbital on the carbocation. This means that there are two possible conformations that can enable the removal of that beta hydrogen. So here, the top conformation places those two large ethyl groups pointing in the same direction. And that means that after removal of the beta hydrogen, those two ethyl groups will still be pointing in the same direction, in this case giving rise to a Z alkene. Free rotation of the carbocation can lead to the lower conformation, which places the two large ethyl groups pointing in opposite directions. After removal of the beta hydrogen, those two ethyl groups will still be pointing in opposite directions, leading to an E alkene. Because the lower conformation places those two large ethyl groups far away from each other, it's going to have less steric strain and be more stable than the top conformation. Because it's more stable, there will be more of this conformation at equilibrium, and that higher concentration will lead to a faster reaction. So the overall outcome is pretty straightforward. In an E1 reaction, the more stable product stereoisomer will almost always be favored. Just as we saw for the SN1 and SN2 mechanisms for nucleophilic substitution, the E1 and E2 mechanisms for elimination compete with one another. The dominant mechanism will be the one that is faster for any given set of conditions. As we saw for nucleophilic substitution, a good leaving group promotes both E1 and E2, and while this is useful information, it's not really useful for differentiating between the two mechanisms. We saw that in nucleophilic substitutions, the structure of the electrophile was extremely useful in determining which mechanism would be dominant. The structure of the electrophile is also useful in determining which mechanism in an elimination will be dominant, but the influences here are more nuanced than what we saw with nucleophilic substitution. Unlike substitution, elimination involves the reaction of two carbon atoms, the electrophilic carbon attached to the leaving group and the beta carbon, from which a hydrogen is removed. It turns out that more substituents on both the electrophilic carbon and the beta carbon promote both E1 and E2. That's because additional substituents lead to more highly substituted alkene products, and a more highly substituted alkene is a more stable alkene. So in this first example, the leaving group, bromine, is attached to a secondary carbon, and the beta hydrogen is attached to a tertiary carbon. In this case, elimination would form a tri-substituted alkene. In the second example, the leaving group, bromine, is attached to a primary carbon, and the beta hydrogens are attached to a secondary carbon. Elimination in this case would result in a monosubstituted alkene. The formation of a more highly substituted, more stable alkene is generally faster than the formation of a less substituted, less stable alkene. So how can we determine the dominant mechanism for an elimination? Well, in general, E2 is still favored by fewer substituents on the electrophilic carbon. And that's simply because having fewer substituents on that carbon would inhibit carbocation formation in an E1 mechanism. E2 is also greatly favored by strong base and an aprotic solvent, which is similar to the effects we saw in an SN2, which was favored by a strong nucleophile and an aprotic solvent. By contrast, E1 is actually quite rare. E1 is promoted by having a higher degree of substitution on the electrophilic carbon, again because it would stabilize the resulting carbocation. E1 is also favored by a weak base in a protic solvent, and that's why E1 is actually so rare. An elimination, by definition, forms a new pi bond, and that new pi bond is less stable than the sigma bonds that were found in the original reactant. In other words, formation of a pi bond is thermodynamically disfavored. In order to work, eliminations need to compensate for that upward trend in energy. And the best way that can be done is by transferring a negative charge from a strong, unstable base onto a good and stable leaving group. And because a strong base favors E2, the E1 mechanism is comparatively quite rare. A big difference between nucleophilic substitution and elimination is that eliminations can actually result in the formation of multiple regioisomers. If we look at this example, we can see a bromine, which is a very good leaving group, flanked by two unique sets of beta hydrogens. To the left of the halogen, there are two beta hydrogens, one of which is drawn out in green. To the right, there are three beta hydrogens, here one drawn out in red. During elimination, removal of the green hydrogen from the left would result in the formation of 2-pentene, and removal of the red hydrogen from the right would result in the formation of 1-pentene. And you can see that the 2-pentene on the left is the favored product. This regioselectivity can be summarized by Zaitsev's rule, which states that eliminations favor deprotonation of the beta hydrogen that leads to the more substituted pi bond. And that's because the more highly substituted pi bond is typically more stable. This implies that eliminations are typically run under thermodynamic control, and that's usually the case. Eliminations often require quite a bit of heat, and that heat allows the reaction to go backwards and forwards, establishing equilibrium. And that means that the more stable product will be the dominant product. Now, there are some exceptions to Zaitsev's rule. Some eliminations will exhibit anti-Zaitsev regioselectivity. The reaction of a tertiary alkyl halide with a very bulky base can force kinetic control in the elimination. If we look at this example, we can see that the major product is not the most highly substituted alkene, so this reaction exhibits anti-Zaitsev regioselectivity. It's simply easier for this big bulky base to remove a beta hydrogen from the primary carbon on the left than the more sterically hindered secondary carbon on the right. In this case, there's also a statistical influence. There are 6 identical beta hydrogens on those 2 methyl groups to the left, but only 2 beta hydrogens on the secondary carbon on the right. So all other things being equal, the base is simply 3 times more likely to bump into one of the hydrogens on the left than one of the hydrogens on the right. Another exception to Zaitsev's rule arises when the reactant has a bad leaving group like fluoride. Again, this forces the elimination to go under kinetic control. In this example, we can see that the formation of the less substituted anti-Zaitsev product on the left is favored over formation of the more highly substituted Zaitsev product on the right. The reason that bad leaving groups like fluoride tend to favor the anti-Zaitsev elimination is rather complicated. In an E2 elimination of a reactant that has a good leaving group, the negative charge is very quickly transferred from the unstable reactive base onto that good leaving group. The ability to stabilize negative charge is what makes a good leaving group a good leaving group. In a similar elimination involving a bad leaving group, the transfer of the negative charge from the base to the leaving group is impeded, and a significant amount of negative charge develops in between the beta hydrogen and the leaving group. In this example, when the base tries to remove a beta hydrogen from the primary carbon to the left of the fluorine, a significant amount of negative charge develops on that primary carbon. When the base tries to remove a beta hydrogen from the secondary carbon to the right of the halogen, a significant amount of negative charge starts to develop on that secondary carbon. And unlike positive charges, which are more stable on more highly substituted carbons, negative charges are less stable on more highly substituted carbons. So when an elimination involves a bad leaving group, removal of a beta hydrogen from a less substituted carbon leads to more highly stabilized negative charge development in the transition state. The more stable transition state leads to a lower energy of activation and thus to a faster reaction. Another way that an elimination can experience anti-Zaitsev regioselectivity is when the anti-Zaitsev elimination would lead to resonance stabilization in the product. And in this case, the reaction is still under thermodynamic control. If we look at this example, removal of one of the beta hydrogens to the left of the halogen would result in the formation of a less substituted anti-Zaitsev product, here shown on the left. Removal of the beta hydrogen to the right of the halogen would result in the more substituted Zaitsev product. But in this case, the Zaitsev product is an isolated diene, and the anti-Zaitsev product is a conjugated diene. And all other things being equal, a conjugated diene will be more stable than an isolated diene, because the conjugated diene has resonance stabilization. So in this case, the reaction is still under thermodynamic control, because the more stable product is still preferred. It's just that the more stable product is not the more substituted alkene. Molecules that have multiple leaving groups can often undergo multiple consecutive eliminations. Let's take a look at what happens during consecutive eliminations on some commonly encountered dihalides. First, we have a 1,3-dihalide. Treatment of this reactant with an excess of strong base will initiate an elimination reaction involving one of those two halogen leaving groups. In this case, the chlorine on the left leaves to form the expected Zaitsev regioisomer, removing a beta hydrogen from the more highly substituted carbon on the right. Another equivalent of base can then affect a second elimination. Removal of a beta hydrogen from the right would result in the formation of a conjugated diene. Removal of the beta hydrogen from the left would result in a strange molecule in which two alkenes emanated from the same carbon. This is called a cumulated diene, and in general, cumulated dienes are very unstable. And we know that in contrast, conjugated dienes are very stable, and so the major product in this case is the more stable conjugated diene. In the next example, we have a 1,2-dihalide, also known as a vicinal dihalide. Elimination involving the bromine on the left would result in the formation of the expected Zaitsev product by removal of the beta hydrogen from the more highly substituted carbon on the right. The result in this case is a vinyl halide, in which the halogen is bonded directly to the alkene. A second equivalent of base could now affect a second elimination. Removal of a beta hydrogen from the right would result again in the formation of a cumulated diene. Removal of the beta hydrogen from the left would actually result in the formation of another pi bond across the two carbons of the alkene, resulting in the formation of an alkyne. And because cumulated dienes are so unstable, the major product will be the alkyne. In the last example, we have a 1,1-dihalide, usually referred to as a geminal dihalide. Elimination involving one of those halogens would result in the formation of the expected Zaitsev product by the removal of a beta hydrogen from the more highly substituted carbon on the left. If you look closely, you can see that this results in the formation of the exact same vinyl halide that was formed in the first elimination of the 1,2-dihalide. And that means that the second elimination, affected by an excess of base, would result in the exact same products, again favoring the formation of the alkyne. The last elimination reactions we're going to look at are the eliminations on alcohols. These reactions are referred to as dehydrations because the molecule that's removed during elimination is water. Remember that the hydroxide group is a very bad leaving group, and the alcohol functional group is also slightly acidic. Treatment of an alcohol with a strong base would result in the removal of the more acidic alcohol hydrogen rather than a beta hydrogen, and that means that strong bases cannot induce elimination on alcohols. Alcohols can undergo elimination of water by reacting them with dehydrating acids. These are special acids that contain little to no water. If you think of a common acid like hydrochloric acid is just hydrogen chloride gas dissolved in water. And even in its most concentrated form, hydrochloric acid is still only 37% hydrogen chloride. The remaining 63% is water. And trying to dehydrate something by pouring water on it is really counterproductive. Dehydrating acids like sulfuric acid and phosphoric acid contain little to no water. These acids can pull water out of an alcohol, and in the process dilute themselves. And you might remember from general chemistry that dilution of a strong acid is exothermic, and the release of that heat energy helps to drive the elimination forward. So in this example, you can see we have a tertiary alcohol reacting with sulfuric or phosphoric acids to form an alkene via the expulsion of water. If we look at the mechanism, we can see that the first step involves the protonation of the alcohol with that strong acid. This forms an alkoxonium ion and redefines the leaving group, transforming it from hydroxide, a bad leaving group, into water, a very good leaving group. The conditions in this reaction are strongly acidic, and that means there can be no strong base present. The lack of a strong base and the protoconditions combine to favor the E1 mechanism in most cases. And that means that the next step is the expulsion of the leaving group to form a carbocation, and then the last step, removal of a beta hydrogen with a weak base to form the pi bond. The acid-promoted dehydration of an alcohol can affect both E1 and E2 reactions. In fact, this is the one time where E1 is actually rather common. E2 typically only occurring on primary alcohols that would form an unstable primary carbocation. The acid-promoted dehydration of an alcohol can sometimes give rise to unexpected products. If we look at this example, we start with a primary alcohol, which would actually undergo an E2 elimination to give 1-butene. Under these strongly acidic conditions, the initially formed alkene can undergo protonation to form a carbocation. That carbocation can then reform an alkene by losing a beta proton from either side. Removal of the beta hydrogen on the right would result in the reformation of the originally formed monosubstituted alkene. Removal of the beta hydrogen from the left would result in a new disubstituted alkene. The new disubstituted alkene is more stable than the originally formed monosubstituted alkene, and because it's more stable, it ends up being the major product. The rearrangement of the initially formed alkene into a more stable, more highly substituted alkene is called alkene walking, and it's very commonly encountered in the acid-promoted dehydration of primary alcohols. Alcohols can also be dehydrated under non-acidic conditions, using a special reagent called phosphorus oxychloride. Because the reaction is performed in the absence of a strong acid, rearrangement of the initially formed product via alkene walking is avoided. The reaction is typically run in the presence of a weak amine base like pyridine. If we look at the reaction mechanism, we can see that we're once again transforming the poor hydroxide leaving group into a better leaving group. In the first step, the alcohol acts as a nucleophile, attacking the highly electrophilic phosphorus of the phosphorus oxychloride and displacing Cl-. The resulting intermediate is then deprotonated by pyridine or some other weak base to set up the elimination. In this example, a beta hydrogen is removed and the rather strange phosphorus leaving group is expelled via an E2 mechanism. If you take a close look at the leaving group that was expelled in that last step, you can see that it's actually a superior leaving group to a hydroxide. The electronegative oxygen and chlorine atoms spread out the negative charge via induction, and more importantly, the phosphorus-oxygen double bond introduces resonance stabilization and spreads out the negative charge over both of those oxygens. And it's the stability of this leaving group that drives the reaction forward. This reaction is effective for both E1 and E2 reactions, but the E2 is far more common. So we've seen that the SN1 and SN2 mechanisms for nucleophilic substitution compete with one another. And we've also seen that the E1 and the E2 mechanisms for elimination also compete with one another. Because both reactions involve the expulsion of a leaving group, both elimination and substitution also compete with one another. So here I have a table that summarizes all of the parameters that affect the relative rates of reaction for SN1, SN2, E1, and E2. Understanding the summarized information here will enable you to determine which of the four mechanisms is dominant for a given set of conditions. Let's start with the easy ones. If the electrophile has a leaving group attached to a methyl carbon, the reaction will be SN2 all the way. SN2 is extremely fast on a methyl carbon, SN1 is extremely slow, and you can't have an elimination without a beta hydrogen. Primary electrophiles are almost as straightforward, giving SN2 in most cases. The only exception is when a strong bulky base is used, which prevents nucleophilic substitution and promotes the E2 reaction. Near the bottom of the table, we can see that when the leaving group is attached to a vinyl carbon, that is, a carbon involved in an alkene, only E2 can occur. Vinyl carbons are sp2 hybridized, and both SN1 and SN2 are forbidden on an sp2 carbon. And E1 is just very rare to begin with, and that leaves E2 as the dominant reaction, generally giving alkynes. When the leaving group is attached to a benzene ring, or an aryl carbon, SN1 and SN2 are again out. The carbon atoms of a benzene ring are sp2 hybridized, and again, SN1 and SN2 reactions are forbidden on sp2 carbons. What actually happens is a reaction we didn't cover here, called an E1CB reaction. But all we really need to worry about here is that none of the four mechanisms of SN1, SN2, E1, or E2 will occur when the leaving group is attached to a benzene ring. In the middle of the table, we can see that tertiary carbons with a leaving group attached will generally favor SN1 when treated with a weak nucleophile and a protic solvent. The reaction will favor E1 in the instance of an acid-catalyzed dehydration of an alcohol, and E2 can be favored using a strong, bulky base, typically in an aprotic solvent. And that leaves secondary carbons, as well as allylic and benzylic carbons, as being the most complicated. In those cases, SN1 will be favored by small, weak nucleophiles in a protic solvent, SN2 will be favored by small, strong nucleophiles, typically in an aprotic solvent. E1 will again only be generally seen in the acid-catalyzed dehydration of an alcohol. And E2 will generally be favored when using a strong, bulky base that prevents substitution.